Hello everybody, my name is Meriç Büyükkoyuncu and I'm a mechanical engineer. Today we are going to make a validation of nonlinear buckling analysis of sub-stiffened plates. When we are doing that, we will use the JohnsonCook plasticity formulation. And also when we are doing that, we are not going to apply the eigenvalue buckling analysis step. We will use faster and easier method to find the ultimate buckling load, because today we are going to find the ultimate buckling load, but with this method we cannot find the critical buckling load. So let me introduce our article. You can see our article name, and we will validate this case. This is called specimen B, and also we are going to use this article to find the JohnsonCook plasticity properties, let's say, and you can see this name and the other. If you have access, you can download them. If you cannot, you can watch the video. So let's close this, and first of all let me introduce the plate, and let me show you first of all. And this is our plate, and in this plate the sub-stiffened, the normal stiffeners and the sub-stiffening are used. So in this article, the top and bottom are clamped, but at the top there are some fixed displacement. As you can see, ux and uy and uz are restrained in their direction, and also rotation x and rotation z are restrained. But in the bottom, and only uz is restrained, and there will be a displacement and through upward direction as at 3 millimeters. Left and right edges will be free in the space according to the article. And also there are some dimensions that we are going to use, and there are 3 main stiffeners and there are 12 sub-stiffeners, and you can see the properties. The plate properties are here. And also our plate, our total geometry will be nearly 2 kilograms. So before we go to there, let me show you. In this article, the aluminum T351 is used, and where is that? Here you can see. And also it is made in Abacus program, but I don't have any Abacus access. In this article, Ramberg-Osgood plasticity formulation is used, but I cannot find the Ramberg-Osgood formulation properties and values, so I'm going to use the Johnson-Cook formulation. I think they will be very close. So let's take a look at the Johnson-Cook formulation, and there are 3 terms. One of them is about stress and strain. The other one is related with the strain rate. So Johnson-Cook formulation is here, and the constants of the Johnson-Cook formulation for our aluminum is given here. And also, where is that? Yeah. Material properties of the aluminum is given here. So we can neglect the second and third term, as you can see here, because we don't have any, we have nothing to do with the strain rates, and also our temperature is not higher for the case. So these becomes the one. So Johnson's Cook formulation is become just this. And also it is very similar to the power law. Actually, this is the same structure with the Ludwig power law, as you can see here. So the equation becomes that if we want to find the strain, I just change the equation. You can see that here. So according to the article, they are given as like this for our aluminum, and also yield strength is 346 and ultimate strength is 476, as you can see here. So let's okay. So at the end of the analysis, our results will be like that. So we are going to sketch the load and displacement curve. We will try this. So let's start with ANSYS. Go to the static structural and please carry it on. Okay, right click on the engineering data and say edit. So go to the engineering data sources and find the aluminum alloy. Please edit. Go back to the engineering data sources. The density will be 80 and also Young modulus will be this value. Okay, we defined the properties, but we didn't define the plasticity properties. So we can use the multilinear isotropic hardening, and please carry it on to the aluminum. You can find it in the plasticity. And we can enter the strain and stress data, but I cannot find them for the Ramberg-Osgood or the Johnson-Cook formulation. So I will try to find them with using Excel. So please go to the Excel and have a stress and strain case. We will write this formulation for the stress and strain, but the stress and strain data should be started in the plasticity point in the ANSYS. This is the rule. Strain should be 0 and stress should be yield stress at the beginning. So we can create the formula. So there will be some stress values. So minus 299 divided by 475, and also 1 over 0.406. Okay, we created the formula and we have to define the stress values. So please choose 2 of them like this and pull it until the ultimate stress 476. Okay, you can pull the strain formulation. Okay, so we are going to copy them into the plastic strain data. So okay, our plasticity data are ready, so we can continue to the model. Let's close it. Today we are going to use just static structural to find the ultimate buckling load. but we cannot find the critical buckling load with this method, but it is very fast according to the other method. If you want to find just ultimate buckling load, you can use that. So when we are doing sketching, please sketch same with me, because I will define a lot of parameters, a lot of dimensions, so you can get confused. So that's why please sketch the same with me. So okay, click on the XY plane and click the new sketch, and let's take a look at. Go to the sketching and select rectangle. Oh, by the way, let's define the units as millimeter. So go to the dimensions, so this will be, and this one, and this one 444 40. Let's remember again. Yes. Okay, go to the concept and say surface from sketches to make this shell, and thickness will be 1 point. This one. So we will create the stiffeners, the main stiffeners. So go to the YZ plane and click new plane. So and go to the transform and say offset Y. This offset will be the half of the plate thickness, so that is and also there is another transform in the Z, offset Z, minus 200. So say generate and go to the plane 4 and say new sketch. Let's take a look at. So there is a little bit difference. Go to the modeling and sketching and click on the rectangle. Please start it from the new coordinate, so there should be a difference between the plate and the stiffener. So go to the dimensions, and this will be that, and the height of the stiffener is 28 millimeter. So okay, say generate and go to the concept and go to surface from sketches, click sketch 2 and say apply. Thickness will be 2.8 millimeter and say generate. So as you can see, our stiffeners is ready. So let's make a pattern. Choose the stiffener and say apply. Direction can be created like this. So offset is 167. So let's create another pattern. So change the direction and say apply. So our main stiffeners are ready. So let's define the sub-stiffening and go to the plane 4 and say new plane. So there will be a offset in the Z direction. So that will be minus 31.9. So let's say create and let's save it. So go to the plane 5 and please click new sketch and say look at. we are going to create the sub-stiffeners. So go to the sketching and click rectangle. And go to the dimensions, and that will be 590 millimeter, and the height will be 8 point. Oops, I'm sorry. Where is that? Oh, okay. 8.7 millimeters, and go to the concept and surface from sketches. Please select sketch tree, and thickness will be 1.4 millimeter. So click on generate. So we need to create the pattern. So choose this sub-stiffener and select the direction, and that's now the offset will be 25.8, and there will be 4 copies. Okay, so let's create another plane, and so click on the plane 5 and say new plane. So what was that? Okay, offset Z. There will be a transform in offset Z, 9 millimeter. I'm sorry, please choose the plane 4 for it. So it is here, and let's go to the here and create a new sketch. The same process. Actually we could do it easier, but we started like this, so let's continue. Go to the concept and please select the sketch 4, and the thickness will be 1.4 millimeter. So another sub-stiffener is ready, so let's create pattern. Okay, 4 copies, and yeah, there are two sub-stiffeners are left. So to create them, let's create pattern and select this one, apply direction. Okay, and say generate here, and also create another pattern. Choose this one, and okay, now our plate is ready, as you can see. Now please click on the share topology so we can merge the nodes and say generate. So we can close the design modeler. Let's save it. So close it and right click the model and say refresh. So right click on the model and say edit. So let's define the material. So go to the mesh and you can use uniform mesh for 10 millimeter. If it doesn't converge, you can use 5 millimeter. So our mesh is ready. Now let's create a connections. Please say manual contact region. And first of all, we need to create the name selections. So let's go to there. And, okay. So scoping method will be worksheet. And please right click and add row. That will be mesh node, criterion, location y, and equal. The value will be 590. And as you can see, these are top nodes. So let's create another name selection. Value is 0. Say generate, and as you can see, these are the bottom nodes. So we need to define the edges to create a contact. So these edges will be located at this value, and the stiffeners edges are selected. So as you can see, and also we need to define the face to create a contact. This value 0, and the base plate's face are selected. So go to the contact again and go to the name selection and select the target. Let's make it beautiful. Okay, let's select the face for the target and select the edges for the contact. So these are selected and the face is selected. So contact is created. Now go to the static structural and let's create the boundary conditions. So as you can see, top is almost fixed. So that's why top nodes are 0, 0, and 0. And also let's define the rotation for the top. Only rotation Y is free. Okay, so go to the nodal displacement for the bottom nodes, and just only Z component is 0. Go to the rotation, and for the bottom nodes only rotation Y is free. So also and there is a 3 millimeter displacement for the bottom nodes going to upward. So please select the bottom nodes and create 3 millimeter displacement. And now in the solution we want to see the total deformation, von Mises strain, and also von Mises stress. But we haven't created the nonlinear properties for the analysis. So go to the analysis settings. So let's create the substeps, and auto time stepping will be on. And let's begin with the 50 substeps. If it converge, you can decrease the 3 substeps. The maximum substeps will be 500. I believe that this will converge. To open the geometrical nonlinear trees, please click on the large deflection and choose on. And also we need to define the stabilization to converge the solution. So please say constant, and we can define the energy dissipation ratio as a 0.05. I believe that that will converge. In ANSYS 2000, by the way guys, in ANSYS 2020 you can use the program control because it really works perfect. And also if you cannot do the Excel case, you can see the Excel file below in the comments. And also, where is that? You can see the A, B, and N values. In ANSYS 2020, there is a power law like this formula, and you can enter the 399 megapascal for the initial yield stress, and you can enter the N for the I don't remember the case, but there's one thing left to enter, so you can use this value. And you don't enter this value, but you will define the ultimate stress, so this will be used in as a ultimate stress. So you can use this in ANSYS 2020, by the way. So let's continue with our case. So our job is done in analysis settings, and also you want to see the load and displacement graph. So that's why I'm going to create new chart and table. So please click on it. So by the way, to see the force, I will define the force reaction probe here. Okay, this force reaction will be created for the, where is that, for the 3 millimeter displacement. So please choose this boundary condition as a 3 millimeter here, nodal displacement 3. Go to the chart, and I want to see the nodal displacement 3 versus force reaction. Please select both of them and say apply. It is not selected. Okay. Okay, this cannot be edited right now because it's not solved. It is not be solved. So let's solve like this, and we can define the chart later. Please go to the, okay, say cancel, and please click on the solve. It nearly takes 30 minutes, maybe 45 minutes according to your computer, so please wait. Okay, it is solved, and let's create the chart. Please select both force reaction and nodal displacement and say apply. Choose nodal displacement in y direction as an x-axis. Please omit the time, omit the other reaction forces, just see the y. And okay, let's go to the, you can see the tabular data here, or we can go to the graph. So let's make it bigger. So as you can see, there's a graph. In the upper limit one was 242 kilopascal. Actually, it is between 2 and 2.4 millimeters. So let's take a look at the article for our plate. So it is very similar in our case. So let's go to the results, and the ultimate buckling collapse load will be between these values. So our value is very close to them, and also our shape is similar. So let's take a look at our plate's shape, because graph is very similar. So go to the total deformation and let's take a look, and let's close the stiffeners. So go to the total deformation and you can see the half wave here. It is very similar. So that will be better, yeah. So we can say that our method is validated right now for the sub-stiffening theorem. It is really working here. So as you can see, it is really good. So if you have any comments and if you want to ask anything, you can ask me in the comments. And thank you to watch this video. So have a nice day.